Welcome back. So what we're going to do in this vignette is we're going to try to set the stage for our first exercise and a feeling for the organism. As you know, the plan is to try to understand what limits the rate of bacterial growth. And as part of that, I want to try to give an introduction to the broad sweep of what now goes under the name of dynamical systems. But for our purposes today, we'll be trying to understand the laws of population dynamics. And to do that, we're going to start out by thinking about the growth of a bacterial culture. We've already talked about what I consider to be one of the mysteries of the world. As you take some water, you add a little carbon and some salts and put a single cell in it at 37 degrees and let it shake, and 24 hours later you'll have 5 times 10 to the ninth cells in your 5 mLs of growth media. So the thing we're going to do is try to understand the dynamics of that growth, and to do that we're going to use what as I say, this will be our first introduction to dynamical systems. But the idea of a dynamical system, to my mind, it really goes back to Newton. In some ways, the great idea that he had was this notion of laws of motion. And it turns out that paradigm has proven much more general. In other words, yes, we think about F equals ma and the laws of motion for material bodies in the sense of mechanics. But in the time since, we learn about the dynamics of the electromagnetic field, and then we learn about the dynamics of the wave function, and we learn about the dynamics of populations, and dynamics of economies, and many, many other things. And all of these can be written in some sense in the form of dx by dt, where x is some vector, is equal to some vector f of x and t. So, this is like the most general version of a dynamical system for my purposes for the moment. And really what it's just telling us is it's telling us the law of the dynamics of x of t. So this is the trajectory of the vector x of t over time. So we're interested in trying to write down some rules that help us think about these kinds of problems. So the first example that we're going to think about is growth of a population of cells. And this will permit me to write down sort of the generic way that we're going to think about all problems of this type. Was that we're going to say the number of cells now is equal to the number of cells before, and then plus some probability, I'll come back to that in a moment, of doubling, and then times the number of cells. So this guy is the number of cells at time t plus delta t, and I'll just generically hold to this idea of using delta t as a way of describing a little bit of time. This is the number of cells at time t, and this is the probability of a cell division in time interval delta t. What do I mean by that? So let's look at the units. This thing is the rate constant, and it has units of 1 over time. And so if you take k times delta t, that's dimensionless, and for small times, k delta t is the probability of the event described by that rate constant happening. And I really urge you to consider this as a different way of thinking about the meaning of rate constants. So at any rate, k delta t is the probability of a cell division event, and then I multiply by n because I have n candidates for doing cell division, and so the total number that do divide is the probability of a division times the total number of cells. So this is basically our growth law. Now I can always do some massaging on this thing, which is I can rewrite it in this form. And that thing is a shorthand notation for a differential equation. And just like in biology, there's all sorts of shorthands. Um, this thing has got a shorthand notation, which is dn by dt. So I'm being a little sloppy here because I have to take the limit in which delta t goes to 0. But dn dt is the rate of change of number of cells. It's basically the growth velocity, if you like. And you can see that that's equal to k n by k times n dt, n of t. So what we've done is we've written down a growth law, which is the law of exponential growth, and that growth law that growth law will be central to many things that we're going to do this in this course. So this tells me the rate of change in the population over time. And let me make a little bit of an aside. So we're going to be interested in writing things in the natural units of the problem. And I'm going to make the distinction between pipetter's variables and natural variables. And the point here is that there's a natural time scale in this problem. So the natural time, quotes, is 1 over k. In other words, that has units of time, and it's the intrinsic time scale of the problem. And so I could always rewrite my equation in dimensionless form by dividing through by k. So I have dn by dt, and that's equal to n. So I could rewrite this as dn by d tau is equal to n. So this is the dimensionless form of my growth equation. Now you might be saying to yourself, well, what purpose does that serve? But the purpose it serves is it calls our attention to the fact that there's an actual scale that we can know about this system. In other words, if I were to look at the problem, you were to offer me the equation that I have up here in the box, if I were to look at it, I would say, oh, well, the time scale over which things happen is of order 1 over k. That's what I would know kind of a priori, because that's the natural time scale of the problem. So what kind of solution does this correspond to? Well, we have dn dt is equal to kn. So I can do separation of variables. So I can divide both sides by n and multiply both sides by dt, if I'm being a little bit sloppy here. And then I will integrate. Okay, and I'm hoping that you'll recall. Let's see here. I'm going to add a page. Just bear with me for a second. I've got to grab some of my work and move it. Okay, so the bottom line is that this first piece is going to give me log of n over n naught, and the right hand side is going to give me kt. And so if I exponentiate both sides, what I'm left with is n of t is equal to n 0 times e to the kt. And this is this super important solution for one of these exponential growth problems. And what it says is that the size of the population is going to grow exponentially in time. That's what this thing says. So if we were to plot the size of the population over time, this is the kind of thing that would come out of it. So, just to try to remind you, the top guy here, this is telling me the rate of growth as a function of the size of the population. So the bigger the population gets, the faster the growth rate. So that's what our differential equation, this equation, told us. Then what I did is I solved that equation. That tells me the population size is a function of time, and that's what's plotted here. And you can see that that thing is growing exponentially. Now let's try and put that in perspective. Let's answer a question. How long for the population to have a mass equal to that of the Earth? And this is something that I think is really, really relevant to the moment that we're living in right now, and the whole reason that I'm annoyingly doing this class online, remotely, with no one else in the room, looking out the window here in San Francisco. Um, the reason I'm doing that is because we have an exponentially growing population of the coronavirus wandering around on planet Earth. And in fact, on one of the homeworks, I ask you to consider the total mass of coronavirus on Earth right now. And in a way, we're going to pursue that question here, but in the context of bacteria. How long would the population, given a typical growth rate, take to have a mass equal to that of the Earth? So, so first thing, let's actually remind ourselves of what the doubling time is. So the doubling time would be 2 times n0 is equal to n0 e to the k t double. In other words, I'm saying at the time t double, the number of cells in the population will be twice the number that we started with. So that's a doubling time. So I can use this. This can be rewritten as 2 is equal to e to the k t double. Taking the log of both sides gives me a log 2 is k t double. And therefore, t double is equal to 1 over k times log 2. Or k is equal to log 2 over t double. So I remind you that log 2 is of order 0.693, and t double will be something like few times 10 to the 3 seconds for our bacteria. And this implies that I'm not going to work it out, but k is equal to something like 1 over 5,000 per second. That's what we find for k. Now, to let me see here. Let me move this to the next page. Cut. Sorry, just trying to do hygiene on my notes here. So if I want to find out how long it takes to have my bacterial culture equal the mass of the Earth, then what I want to do is I want to figure out, I want to solve for the t, let me call this t star. I want to solve for the t star that gives me m Earth after that amount of time. So the mass of the Earth, I'm gonna be very loose here. I'm gonna say this is 10 to the 24th kilograms, and the mass of a cell is 10 to the minus 15 kilograms, and that's e to the k t star. So this tells me that 10 to the 39th is equal to e to the k t star. So log of 10 to the 39 is equal to k t star, or t star is equal to 1 over k log of 10 to the 39, which is equal to 39 over k log 10, and log 10 is 2.3. That's something that we're going to carry around and use repeatedly. So so let's see. So I guess my final flourish here is just to note that 1 over k is equal to, what did we say from up the page? So 1 over, so this will be something like 5,000 seconds. So this implies that t star is equal to 5,000 seconds times, let's call it 40, times 2.3, something like, let's see, this gives me 20 times 10 to the 4 times 2.3, so around, let's say 5 times 10 to the 5th seconds, so something like 5 days. Okay, that was the insight that I wanted to provide, is the power of exponential growth. So what have we done, just to recap thus far? My first example is that I wanted to think about the growth of a population of cells. I used this as an opportunity to introduce a paradigm that we're going to repeatedly use. And that paradigm is this, which is amount of stuff now is amount of stuff before, plus whatever we added, minus whatever we took away. That's going to be a paradigm we're going to come back to again and again and again. It's in a way a conservation law, and it's the way we reason out dynamical systems often. Not always, but often. So that led us to this law of exponential growth. I commented a little bit about dimensionless form. We solved that equation. And then as an exercise, we asked how long for the population to have a mass equal to that of the Earth. And what we found is something on the order of 5 days, something like that. So clearly this notion of unbounded growth is not an appropriate picture in the long time limit of what's going on with either the coronavirus or with bacterial cells. And so what I want to do now is I want to talk about a second example, and this will be brief, and I'll leave the rest of it to all of you in homework. But this is a phenomenological model known as the law of logistic growth. And let me use this as a moment to advertise the virtue of phenomenology and phenomenological laws. So, in mid-1600s, Hooke articulated the law that bears his name, Hooke's law. And what does Hooke's law say? It says that the force is linearly related to how far the system is pulled out of equilibrium. In the early 1800s, people like Boyle and Gay-Lussac, I've already mentioned this, they articulated the ideal gas law, or the various gas laws, like PV is a constant at constant temperature, and so on. Those are phenomenological. When I say phenomenological, it's not a dirty word. It's a statement. It's a compact statement of what we have observed in the world around us. And that phenomenological law, it demands two things of us. One is it demands us to explore the consequences of that law. There's lots of consequences of the ideal gas law or Hooke's law. And it also demands a deeper explanation. Where do those laws come from? So the logistic growth law was proposed as a simple way to think about limiting the unchecked growth of an exponentially growing population. And so the idea here is that we write the number of cells in the population has a rate of change given by Kn, and then 1 minus n over k. So, to write it more sort of transparently, this is written in this form. So what does this say? This says, this term says growth, and this term says decay. And there's a really nice way for us to think about this, and that's shown here, where what we're looking at is a plot of the two terms. So the green line here, this piece, that's this term. It's basically the linear growth of the population as a function of population size. The red curve is this piece. It corresponds to this term. It has a minus sign. So whenever green is above red, that means the population is growing. But whenever red is above green, it means the population is shrinking. So that's quite cool and powerful, because what it tells us is that there's going to be some fixed point. There's going to be some particular value at which the population's neither growing nor shrinking, and that's when n is equal to k. You can see that because when n is equal to k, then this term vanishes, and so the rate of growth of the population is 0. Now, just a few words about how to solve this, although I'm gonna really leave it to all of you in the homework. The strategy will be the same as what I wrote down before. So solving logistic growth asks us to once again do what I'm going to refer to as separation of variables. So I will write n 1 minus n over k, and that's equal to k dt. And so I need to integrate this thing. And this is just an aside. One of my favorite methods, actually, that I learned about when I first learned calculus and literally had no idea that it was coming, was the method of partial fractions. So, the idea here is that you want to take this denominator and turn it into two simpler denominators. And the way you do that is basically you multiply. You give the common denominator on the right-hand side, and then you balance powers. And the reason that's useful is that once you've done this, then you know how to do these two integrals. They're both logarithmic, and so the result is relatively straightforward. So I'm going to leave that as a homework. So what do I want to say is, if you carry out that program that I just suggested, which is straightforward, a little bit algebraically subtle in the sense that you need to be a little careful, but you'll get this growth law. N of t is as shown in the right hand side, and when you plot this, the population size as a function of time, initially it is exponential in this regime. So this would look exactly like an exponential growth, but then it turns over and saturates, and it saturates to the value k. So to summarize, what we've accomplished here is we've given our first introduction to dynamical systems, which is going to be a very, very abundant theme in everything we say in this term. And then we also examined dynamical systems in the context of bacterial growths, first with exponential growth, and then which is unchecked. And we showed through a simple example that population grows out of control. In less than a week, you have a mass equal to the mass of the Earth. And then we remedied that phenomenologically in the form of the famed logistic growth law, that I took as an opportunity also to give a plug for the idea of the power, the usefulness, the niceness of phenomenological thinking. And it's something that I believe is really important for biology. So with that, I'm going to call this quits, and